Hey everybody, welcome back. Today I wanted to dig into a topic that is very pertinent to modern day guitar pedals, but that doesn't necessarily seem to get a whole lot of specific attention out there on the internet. And what I'm talking about today is microcontrollers. In the history of audio, guitar audio in particular, there are certain inventions or developments that have really kind of made what is possible for the DIYer take a big leap forward. The transistor was certainly one of those, going from vacuum tubes to transistors. Op amps is another. The development of things like MIDI has been really big. The ability to get low-cost PCBs really easily, and microcontrollers certainly fall into that realm. And when I'm talking about microcontrollers, there is a whole big class of microchips called microcontrollers. For example, here's one. This is the AT-Tiny 85, which is one that I use really frequently for things like relay bypass, for my tap tempo module for the PT2399, anything where it's performing a pretty simple function. You can get them already mounted on little boards like this. This is what's called the DigiSpark Pro. It's just an AT-Tiny 85 on there with a USB connector and a voltage regulator and stuff. And I've used that for a couple of non-guitar projects. But some of the microcontrollers that you might be most familiar with are the Arduino microcontrollers. This right here is an Arduino Nano, which has the square chip there in the middle is the microcontroller. It's got some support chips on it for supporting USB and for some of the onboard LEDs and the onboard button for reset. And this is actually the one we're going to be talking about today. But I will do more videos on microcontrollers that will actually go into some of the other ones. But the ease of use of the Arduino ones makes them really easy to get into, super low barrier of entry. They're available everywhere for really cheap. But microcontrollers can be far more complex. You can find them mounted on what are called development boards so that you can play around with them. You can develop code that can then be used on a deployed board where you don't have all of the surrounding stuff. For example, this here is an ST micro development board for a Cortex M7 class microcontroller, and as you can see there, the chip has a whole ton of pins. I think this is a 144 pin chip, but anyway. You can get microcontrollers that are really super beefy. In fact, the Cortex M4 and M7 chips even have onboard DSP instructions so that you can do some basic DSP programming on there as well. But with that said, we're going to move over to the computer screen so that we can talk a little bit more about how you can actually go about taking one of these guys and actually doing something with it. Okay, so before we get going too much into how to actually do our first example project on our Arduino Nano, let's talk a little bit about what a microcontroller actually is. At its most basic, a microcontroller is a device that has pins that can either sense a signal or can output a signal. And based on what it senses on the input, you can code up different logic to make different decisions about what other output pins are doing. And when you're looking at a microcontroller in a datasheet or other reference documentation, the one thing that we look at a lot is called the pin map, or the pinout, as it's called here. What this does is it describes to you what each pin is capable of, or what its function is. So to start, we have our positive voltage here, which is going to be up to 5 volts for most microcontrollers. Some only have a maximum voltage of 3.3 volts. And pin 4 is ground. Okay, so those are really easy to understand. They're out of the way. But these other ones, you can see that these other pins all have multiple possible functions. That's one of the great things about a microcontroller, is that the different pins can be assigned for different functions. So let me explain a little bit of what is going on here. The PB2, as it's called here, means that pin number 7 of the package is the port B pin number 2. Okay? You have to remember that in most digital logic, everything is 0 indexed, meaning it starts from 0. So the very first pin on port B is going to be PB0, which is on our pin 5 package. You'll notice that the numbering doesn't really make sense. That is all due to how the designers laid it all out inside of the chip. But what does port B mean? Well, internally, the microcontroller has to keep track of where all the different pins and their functions are, and so it has different ports, and each port can only support a certain number of pins. So, for example, we only have port B on this device, but if you get to a larger microcontroller, you can have microcontrollers that have ports A, B, C, and D, each with multiple pins. And it just has to deal with the internal logic. You don't really have to worry about it. More than anything, you just need to make note of what these pin assignments are for when you're trying to assign them a function in the code. Okay? But you also see that we have PCInt is specified here. That stands for pin change interrupt. So if we just had this assigned as a normal digital input or digital output, it would just be, we could assign the pin to go high or low, or we could read if the pin was high or low. But with pin change interrupt, if we make it so that this pin 7 is a pin change interrupt, then what happens internally is anytime the voltage on this pin transitions from low to high or from high to low, it sets a little flag internally saying, hey, something changed. And you can set code in there so that as soon as something changes, it makes a decision to do something else. And for something like a relay bypass, that's exactly what you want to do. Now, in addition to that function, you'll also see that we have A1 here. Okay, so A0, A1, A2, A3, those are analog inputs. Okay, and what happens is that you can actually sample the signal on the pins that can be assigned as analog inputs so that you can do things like read a voltage. Now you may be thinking, great, I can put my audio signal in here and I can do some basic digital signal processing. While that's technically true, on a lot of these smaller microcontrollers, the analog to digital converters are not they're not terribly fast, but they also have very low resolution. Okay, this class of microcontroller is what's called an 8-bit microcontroller, which means the biggest number it can represent is 8 bits, which means that you would only get 8 bits of resolution in your analog signal when you're sampling it. Okay, so not great for actually processing audio, but really awesome for hooking up a potentiometer and using that as a control voltage. So if you wanted to use a potentiometer to control the rate at which an LFO is going, or if you want to control the brightness of an LED or something, the analog inputs are really, really important that way. These other boxes that we see here are for serial communications. Okay, that's where serial communications basically just means that the microcontroller can talk to another serial-enabled device and they can exchange information back and forth, which is really handy for doing things like reading or writing to or from memory, or if you are wanting to control, say, something like a switch IC or, other such serial-enabled devices. A digital potentiometer is going to be a good example of one of those serial devices that a microcontroller can talk to. In fact, if you go look at something like the Taptation PT2399 tap tempo module, that's exactly how it works, is that it uses a potentiometer on one of the analog inputs, and the microcontroller talks to the digital potentiometer over serial to make a decision as to what the digital potentiometer's resistance should be. So this is what a pin map looks like. But because we're not working on this one, let's take a look at the pin map for the Arduino Nano. And this is a simplified version. You can see we have many more pins. They have their other functions here. We have some pins that are labeled as D with a number. We have others that are labeled as A with a number. These are digital only pins. So these pins over here, digital only. Any of the analog enabled pins are going to can be assigned to be either digital or analog. They're dual function. They're not only analog, but these are the only ones capable of analog. So on the Arduino Nano, you can see that we've got plenty of pins. You can see that, they've got the port assignments over here for internal referencing, and there's some other stuff going on too. In fact, with the Nano, you can get much more complicated. This is a very simplified pin map. If we wanted to look at one that was a little more complex, this is what it would look like, but we're not going to bother with this one, okay? But just be aware that just because we're looking at a simplified one doesn't mean that we have fewer functions. It just means that we're only looking at very specific functions in this particular case, which is really just which ones are digital only and which ones are digital or analog. Okay? So that is what our Arduino Nano's pin assignments or pin map looks like. Now, to get started, Arduino has made it really easy. Not only are the devices cheap and really readily available, but they have an IDE, which stands for Integrated Development Environment, that is actually really pretty easy to use and rather convenient. So you can go download this for free from the Arduino website, and it just installs like any other program. And you can see I've already got a little program that is up here, and we're going to talk through it a little bit. But first, this is a built-in example that comes with Arduino. So once you have hooked up your Arduino to your computer and you've installed the software, you can come up to File, Examples, Basics, and Blink. Okay, so this is Blink, and what this is going to do is this is going to blink the onboard LED that is on our Arduino Nano board. Okay, so you can actually see that it says on the Uno, Mega, and Zero. This also works for the Nano, that there's an LED attached to digital pin 13. Okay. And so the way that the code gets set up, if you don't have any experience with writing computer code, I encourage you to go kind of read up on some basics. We're not going to get deep into it in this video at all. I'm just going to explain kind of the three main blocks that happen in a typical microcontroller program in Arduino. Now, if you were to use a different code environment than Arduino, say you were to use, something like VS Code, which is another popular programming program, if you will, it's going to be a little different. Arduino is kind of its own language. It's based in C, but they have done a whole lot of work in abstracting a lot of things out so that you don't have to worry about a lot of the really kind of low-level register reading and writing. And we might talk about that a little more a little later. But the three main blocks of a microcontroller program is that you're going to have, there actually isn't one in this program because we don't have to really worry about it, but There is a definition section, which is usually the very first top section. So it would go, right in here. And that's where you are defining all the different variables that you're going to use in your program. Okay, because if you don't have your variables declared, then the compiler, which turns all of your code into the actual binary code that is on your device, it's going to give you an error because it's going to say, hey, I don't know where this should be in memory and how much memory it should take up. So there's the definition section. Then there is the setup section. And the setup function or section here is code that is run the very first time that the microcontroller gets powered up. So this will be the first stuff that it executes is in setup. And then once it has powered up and it's ran setup, then we have what's called the main loop. In C, it's called the main function. Here we just call it the loop function. And the loop function is a block of code that the microcontroller will run over and over and over and over until you remove power from it. Okay, so that's where you write the main body of your program. So let's look at what they're doing here with the Blink program. So we don't have any variables to define because they're using all built-in variables. And in setup, what they're doing is they are defining a pin mode. The pins that you can assign to different values on a microcontroller are referred to as GPIO, or General Purpose Input Output. And the pin mode tells the microcontroller how to configure that pin. So is it going to be an input? Is it going to be an output? Is it going to be an input that is normally at a high voltage? Those are the things that pin mode is going to tell the microcontroller. And you can get more advanced after that and set up things like, if you want to set up things like pulse width modulation or PWM, you can do that as well. That was my soldering iron beeping. So setup is where you configure all of those things so that they get run once at the very beginning to set everything up. And then we move into our loop function. And in our loop function here, because this is just going to run over and over and over, because we want to blink an LED, what we will do is we will digital write, meaning we're going to set a pin to either high or low, and we tell it which pin we want it to write to, and LED built-in, Arduino based on your board knows how to interpret that. And then we say, write it to high, meaning make the voltage high, or 5 volts. Because it's a digital pin, we can only give it one of two values, and that is plus 5 volts, which is our logical high, or 0 volts, which is our logical low. And so after we write that pin to be high, that's going to turn our LED on. And then we're going to delay or wait for 1,000 milliseconds, which is going to make it so that our LED is on for 1 second, and then we're going to write to the built-in LED pin, and we're going to say, now go low, or turn off the voltage so that the LED turns off, and we will wait for another second. Okay? And it just loops through this over and over and over so that as long as there's power applied, the LED is going to blink on, stay on for a second, and blink, and then turn off and stay off for a second, and just do that over and over and over. It's a really basic program, okay? Now that we've got our code, how do we get our code onto our microcontroller? Well, to do that, we're going to come up to Tools here. And under Tools, there's a whole bunch of both tools and configuration stuff that we can do. So the section that we really need to worry about is going to be down here, okay? So first we have to tell it what kind of a board is connected. And so we come over here, because we're using one of their built-in boards, we can go to AVR, Arduino AVR boards, and come down and we have Arduino Nano. Okay, so we just select Arduino Nano, and that tells it we're using an Arduino Nano board. And then for the processor, this is what is the actual microcontroller that is on there, because they made different versions of the Arduino Nano. And for my specific version, because I'm using a clone version from overseas, I use this ATmega 328P old bootloader. Some of the newer, more genuine boards may need to run this one, but for what I have, this is the one that works. Okay. If you are running a different board that has a different processor, you just need to select the right one. Okay. Next, we need to tell it what serial port it's connected to. Now, if you were on a Mac, it would be really nice and list out all the devices for you over here, because of how a Mac enumerates the serial devices. On Windows, it just gives them a useless number. Okay, they start enumerating at COM0 and go up through however many connected serial devices there are. On my computer here, though, I only have one board connected. It's this COM4, and so I select that, and that tells it. So this is saying, here's the board that I'm running, and this is the processor, so now it knows how to package up all the information, and this is telling it where to send all of that information. But then we also need to tell it what utility to use to actually program the device. And for what I do, I have found that AVR ISP Mark II has been the one that works really well for me. Okay? You are welcome to go read about all of these other ones. I'm not going to get into those, but that is the programmer that we're going to use, and we are not really going to talk about anything else in here today, because those are the basics to get us all set up. So now that we've told it where we want it to send the code and how to package it all up, and we've told it what our code is, we go through two steps. The first step is we're going to verify the code. What this is going to do is it's going to run the compiler, which is going to take all of our code, and it's going to turn it from something that we can read into an optimized version of binary code that takes up the minimum amount of space on the microcontroller. Because your microcontroller only has so much space for storing a program or for storing data. It's only got so much memory, and that varies from device to device. So if we click on verify our code, it says down here it's compiling the sketch, and it's got our little progress bar over here. And all it's doing is it's just running its checks. So if I expand this up a little bit here, it says our sketch uses 924 bytes, which is 3% of our program storage space. And then the global variables use 9 bytes, which is negligible, of our dynamic memory. So this dynamic memory is where we're going to be storing data that might change value during the program. Okay, so if you wanted to store like the value of a potentiometer or something, it would get stored in this dynamic memory because it's something that is likely to change over the course of running. So now we've compiled it. And when we compile it, really what we're doing is we're really looking for two things. One, does it throw any errors? And two, how much space does it use up? Because you may be using a program that uses a whole bunch of space and you really need to try and optimize how much space you're using. So there we are compiling. After we compile, we can upload. Now when we upload, it will recompile the sketch for us just in case anything has changed in our code. But once it compiles, then it pushes it to the device and it tells us that it is now done uploading, which means that with our if we apply power to our board and everything, we will see that the code is now doing what it's supposed to in blinking this LED 1 second at a time. I'm going to switch over to the camera now, and I'm going to show that to you. Okay, so here I have my Arduino Nano on a breadboard, and this right here is a breadboard power supply module. You can find them all over the internet for just a few dollars. And what they do is they supply either 5 volts or 3.3 volts to the power rails of the breadboard. They are really handy when working with microcontrollers. And then in addition, you can see I've just got two jumper wires, one for power and one for ground. And right now the power is turned off, but once I apply power to our board, you can see that this LED over here is blinking exactly the way that we had coded it. It's on for a second, off for a second. And it just does that over and over and over as long as there's power, exactly the way that we had coded it in our sketch. Okay? Now this is a really basic example, but it's a great way to verify that you're able to successfully push code to your board and that it's executing the right way. So that then when you start making other changes to your code, you don't have to worry about, oh, did it actually program correctly? You can start looking at the code going, okay, why isn't the code working from a logic standpoint? Next time we'll be taking a look at a relay bypass circuit and the code that goes along with that. And I hope you enjoyed this video. If you're not subscribed yet, I encourage you to do so you're notified when the next one comes along. But until then, thanks for watching and take care.